In this video, we're going to go over the next section covering matter. So let's go ahead and start with our vocabulary. By the end of the section, you should be able to define all these terms and understand what they mean. So in this, they are substance, mixture, homogeneous, heterogeneous, physical property, chemical property, phase, solid, liquid, gas, precipitate, intensive property, and extensive property. So let's go ahead and start talking about substances and mixtures because these are the two categories that we can put our matter into. Now, the difference between this is that for a substance, it's really just a pure sample or a pure amount of matter, and that means that it's made of only one thing. It might be an element or a compound, and we won't get too much into details for this one, but we'll talk more about it when we start Unit 4. Now, you can think of it this way. So if you had a ball pit, that they can be all different colors. But imagine a ball pit that was all a single color. This would be an example of a substance because all these balls are all exactly the same color. And so how that compares over to a mixture is that it's a mixed sample. All right, it's made of different things that they can be similar, but they're not necessarily the same. And so the example of that would be a ball pit with all different colored balls. So you can say these are all balls, they're all very similar, but because they're all a different color, you can say that they're all different from each other too. Now, the two types of mixtures, we can further classify this, and they will be either a homogeneous mixture or a heterogeneous mixture. So for a homogeneous mixture, it's a constant composition. Another way to say it is that it's a single phase or a single state of matter, and it's very difficult to separate. So I know these are all very technical terms, the way to think of a homogeneous mixture. So you can think of either Kool-Aid or maybe something like salt water. So what I mean by a constant composition or a single phase, that means that they're all in the same state of matter. So if you think of the Kool-Aid, it's a drink. There's no chunks in it, and so that because it's all liquid, you can think of it as being a single phase. Same thing for the salt water. Again, it's all liquid, even though there's salt dissolved in the water, and it's very difficult to separate it out with physical means. If you try to scoop it out with a spoon, or if you try to filter it out, it would be very difficult to get it all out. And so that's an easy way to tell apart from the heterogeneous mixtures, because these do not blend smoothly, and the individual substances that they're made of, they remain separate from each other. They don't mix, and it's very easy to separate. So the examples of these that I have, it's maybe a bowl of cereal. The two phases or the two components of the cereal would be obviously the cereal and the milk that goes with it. And then the same goes for maybe Italian dressing. There's the oil part of it, and you know that there's the solid parts that will settle to the bottom if you leave it alone, if you leave it in the refrigerator in the bottle. All right, next we get into the properties of matter. So let's start with the physical and chemical properties and how we can tell them apart from each other. All right, anyway, so we can describe the properties of matter in two ways. They're either physical or they are chemical properties. The difference between these two is that the physical properties, you can observe an object or a substance and you can describe it. And you can do this without changing what your substance is. And so usually this can be reversed very easily. So if you can think of water, you can have liquid water or you can have solid water. It's called ice. And so you can think of switching between the two just by putting it in the freezer, lowering the temperature, going from liquid water into solid ice, going from liquid water into solid ice. And you know that you haven't changed the compound or what the water is made of. You only changed if it's liquid or if it's solid. So that would be an example of a physical change and the physical properties. The chemical changes, they're a little bit more difficult to deal with because you can't just observe it. You have to make a change in the substance to know what their chemical properties are. And so doing this actually changes the identity of your substance. You might change the type of compound that it is, and these cannot be reversed easily. But again, we'll be talking more about that in Unit 4, so just hold on to those concepts for a little while. So some examples for the physical properties that we might have is, the temperature at which a substance boils, that's called the boiling point, or the temperature at which it freezes, that's freezing point. Also, we can have its density, the viscosity, that's the resistance to flow for a lot of liquids. So if you can compare, water or syrup, the syrup would take a lot longer to pour out of a bottle than would the water. And then finally, the texture, however it feels, if it's a smooth surface or if it has a rough surface for whatever substance you're looking at, these are all examples of physical properties. As far as the chemical properties, these are a little bit more complicated to study. And so this would go on with the reactivity of a substance, with its flammability, if it can be lit on fire or not. So you can compare wood as opposed to a piece of metal. You know that wood will burn, but metal will not. The toxicity, if it is harmful to ingest, this comes down to uh, a chemical property is what separates, poison from the food that you eat. And finally, the pH level of it, which is just another way of saying the acidity of it. You would know that lemon juice are very strong acids. All right, but now we can get into the states of matter and just different ways of describing it. We already worked with ice and water a little bit. I talked a little bit about it, but let's talk about their molecular structures. All right, so when it comes to this, um, all the different states of matter, they have very specific molecular arrangements. And so if we start here looking at the solid state of matter, you can see that the molecules are all packed very closely together and they all have a sort of shape. That's because these molecules, they're being attracted to each other and they hold on to each other very tightly. So for that reason, they will hold their shape. That's why you can have a block of something solid, but not a block of something that is liquid. Now, they also have a definite volume because if you notice the space between these molecules, they're already pretty close together. They can't get much closer. So if you try to squeeze them together at the molecular level, you wouldn't get um, much squeezing. So that's why we can say that they have a definite volume. They're not going to expand or they're going to get much smaller very easily. And they cannot be compressed, again, because the molecules are already so closely packed together. Next, we can look at the liquid. So you can see that the liquid, it's really still closely packed together, but they're not as ordered as they were in the solid state. So it's a lot more disordered, but still relatively close together for the molecules. Now for this, there's no definite shape, again, because the molecules are not held in a single place. They move around a lot. And so you can think of this as, the water flowing. If you spill water on the floor, you know that it's going to get anywhere. You're not going to have a block of water. Or if you pour a cup of water, well, that water takes the shape of the cup. However, water and liquids, they do have a definite volume because you can see the space in between all these molecules. They're still pretty closely together, even if they're not being held in place. And so, for that reason, they cannot be compressed either, just like solids were. And finally, we get to the gas phase. And so notice that the particles on this, we have a lot less gas particles in this, and there's a lot more space between all these molecules. That's because these gas molecules, they have a lot of kinetic energy. They're always bumping around and they're knocking off each other. So they're creating space between them because they're always moving so quickly. For this reason, gases do not have a definite shape. They only take the shape of whatever container they're in. So if you can think of a balloon expanding, uh, it has a circular shape because that's the shape of the balloon. Gases also don't have a definite volume. And so, as we'll learn in a later unit and deal with the gas laws, we know that gases will change their volume depending on the pressure being exerted on them and the temperature of whatever environment they're in. But gases are the one exception to the compression rule where you have all this distance between all these molecules. Well, you can very easily push them closer together and you increase the pressure that way. That's how you get compressed air. And if you ever dealt with psi, that's because you're stuffing a lot more air molecules into a smaller space, or you're getting the molecules closer together. And now let's get into the phase changes, or remember these are physical changes that we can go through. So again, we have our three examples. We have the solid ice, and you know that if you were to just take a piece of ice out of the freezer and you set it on a counter on a hot day, you know that after some time it will start to melt and it will become liquid water. All right. And if you take that water and you just leave it there, and again, if it's a very hot day, it will start evaporating into gas and enter the air that we breathe. Right. So these are just simple examples of phase changes. We're just going from one state of matter into the next. In this case, going from solid to liquid through melting, and then from liquid into gas by evaporation. Now, the big thing about physical changes is that these can be reversed. So if we were to start over in the gas phase and just we can set it in reverse and going from steam into water. That process is called condensation. There's a specific name. It's not just reverse evaporation. We have the name condensation for it. And then going from our liquid water into the solid ice, that's the process of freezing. Now, there's actually two more phase changes that you might not be familiar with, or you may just not have thought about them. But we can actually skip the liquid phase and we can go from the solid straight into the gas, and this process is called sublimation. So if you ever worked with dry ice, if you ever had a block of dry ice, you know that it looks very foggy if you ever opened a freezer from it. Uh, and so that what is happening is that the dry ice is so cold and being just at room temperature, that temperature change is so great that it actually skips the liquid phase and goes straight from the block straight into the air, going straight from a solid into a gas. And the reverse of that, that example is not as common, but going from a gas straight into the solid, it's deposition and usually takes a lot, very large amounts of pressure to do that. So for that reason, it's not something that we can easily see, in everyday examples. All right, next up, we have the chemical changes that we can describe. And so, a lot of the times, chemical reactions will completely change the identity of the substances that we are starting with. And these are very difficult to reverse. Not as easily as just taking our solid ice and melting it into water, and then evaporating into steam, and then working backwards. Now, so all these chemical changes are a lot more involved. And a lot of the times for a chemical reaction, you'll take two different substances, in this case, A and B, and through a chemical reaction, you get a brand new product, nothing that you started with before, and you just call it C. And a lot of the times, you can take two different elements and they will combine to form a compound. Now, these new substances, they will always have different properties than whatever you started with. So that's why we can have all these different objects and compounds that are, they're all made of the same basic elements, but they all have very different properties because they're all chemically connected to each other in different ways. Now, some examples of these chemical reactions is, maybe frying an egg, burning of wood, and then rusting of iron. And so, for a lot of these cases, it's very hard to go back from your end product back to what you started with. So, with burning wood, it burns into smoke, it releases heat, and it turns into ash. Well, you can't take that ash and you can't take that smoke and then put it back into a log of wood. All right, same thing for, frying an egg and cooking any type of food. You can't uncook food. You can't go back to your raw product. And for iron rusting, uh, actually, iron is a magnetic metal, but once it becomes rust, maybe if you were to shave off all that rust, then that nail, that iron nail, will no longer be magnetic because it's all rusted out. Now, one of the challenges that we might run into is how do you know when a chemical reaction has taken place, right? If you can't observe a chemical property directly, how do you know when your substances are changing chemically? Well, there's a few telltale signs that we can go by and that we look for in our chemical reactions. So our indicators in here is something like a color change. So in this example, you can see that if we take this yellow liquid and this white liquid, if they combine and they react chemically, then they form a new red product that we didn't start with. And so there's really no source for this red liquid except that these two substances have become something new altogether. So we can have the production of a gas. So if you ever mixed baking soda with vinegar, this is the classic, paper mache experiment. And so it gets really foamy. And the reason why it gets so foamy is because you're creating a lot of gas in that chemical reaction. We can also form a precipitate, and this is another one of our new vocabulary terms. You might not have used it before, but the precipitate is a solid product that forms when you combine two different liquids. So you can see that in this test tube too, that we have the liquid in the test tube and we have some more liquid in this dropper, and when you combine them together, you get this solid white product that starts forming. It looks kind of cloudy, but it is a solid product that is forming from two liquids. And so this is all because we've gone through a chemical reaction. Also, if something produces light, this is usually a form of a chemical reaction. So if you can think of glow sticks, you know that you have the long glow stick, and inside of it you have both a liquid and a capsule inside of the glow stick. And when you break that capsule, then the two liquids start mixing together, and then that type of chemical reaction creates a light. And finally, the last type of indicator that you might look for is, heat being released or absorbed. So two examples on this is, an explosion or fire. This is a big release of energy, and it gets very hot. It releases a lot of heat. So you know that is the product of a chemical reaction. And also, if you ever used these instant cold packs, you're mixing some compounds together, and together they absorb energy. Instead of it making something hot, it starts to absorb energy, and it makes the surroundings cold. And finally, the last way that we can describe our properties of matter is either intensive or extensive. So let's see what each of these are. So for the intensive properties, these are all independent of how much sample you have. And they are very specific properties, and they're defining characteristics of the substance. Now, these intensive properties cannot be changed, and so just this, any type of substance will have this specific set of intensive properties. And actually, they're so unique that you can use these intensive properties to identify substances that you don't know what they're made of, but you want to find out what they are. So some examples of this is the melting point, the temperature at which something will melt, as well as the boiling point, the temperature at which something will boil. Also, the density, even though it's a physical property, it's very specific to the different substances that we might have. And the reactivity of something, if it will react to something, if it is flammable or if it is not flammable. As for the extensive properties, these type of properties depend on the size of your sample, how much of it you have, and they're usually measurements of your substance. And you can very easily change them just by changing how much stuff that you have. The example of this would be something like mass. You know that you can weigh this on a scale. The length, if you have 3 meters of rope, you can cut it down into 2 meters of rope. You haven't changed the fact that it's rope, you just changed how much rope you have. The volume, how much space it takes up. All right, so let's look at this example for our intensive properties. So let's say that you have a piece of metal, you don't know what it's made of, but you do know that its mass is 52.7 grams and its volume will be 5.9 centimeters cubed. Now, from that information, can you tell what type of metal it is? And so, yes, you can, even though you have these extensive properties and they don't really help you to identify a substance. You can take both the mass and the volume of it, and you can calculate the density from it. Now, you know that density is an intensive property, and so knowing this density could tell you what your metal is. And luckily, we also have a table that tells us the density of different types of metal. So we can have gold, silver, and copper, and these are all their very specific densities. So if you take this information, you put into your density formula, we have that density is equal to mass over volume. You substitute in the values that you know, so we know 52.7 grams set over 5.9 centimeters cubed. If you put this into the calculator, you do that calculation, you get 8.9 grams per centimeter cubed. Now, all you have to do is take that result and compare it back to your different densities. So you know that gold has 19.32, silver is 10.49, and copper will be 8.96 grams per centimeter cubed. The only match that this one even comes close to is copper. So from knowing the mass and the volume of your piece of metal, you know what type of metal it is, just because you were able to calculate the density of it and match it to a known metal with a density. And so this is the thing that's really interesting about these intensive properties, that if our problem was different and we had half as much mass and half as much volume, we could still use this formula and we would still get the same result for the density. So it doesn't matter how much of a metal you had in this one, the density would always be correct. It would always be the same. It would always point you to being copper.